So lecture 2. Now, a lot of this material will still feels like a lot of review kind of, but it's really important, so that's why I'm going over these things. So in this lecture, I'm going to primarily talk about non-covalent interactions, okay? You should know what those are, like van der Waals, hydrogen bonds, that kind of stuff. Hydrogen bonding, properties of water, hydrophobic effect, okay? Hydrophobic effect is a wonderful thing that we can use to explain a lot of stuff, okay? So covalent versus non-covalent. Covalent bonds are formal bonds or formal electron sharing between two atoms, okay? And for our purpose, primarily we're talking about sigma bonds, pi bonds, those things, okay? Now, this I'm sure you guys should know, okay? So formal bonds. Formal bonds, when we draw it on chemical structures, they look like a little line, okay? That means 2 electrons, okay? So every line you have 2 electrons. Fine. Non-covalent interactions are more important to us, okay? So non-covalent interactions are electrostatic interactions between molecules or within a molecule, okay? Now, it's electrostatic, it's always electrostatic, it's not like gravity or anything like that, no, okay? It's electrostatic interactions between molecules or within a molecule, okay? There are different types. For example, you got the ionic interactions, okay? Ionic interactions are charge-charge interactions, okay? So 2 charges of the same sign, they repel. Opposite charges attract, simple, okay? Hydrogen bonding, okay? Hydrogen bonding, it's a special type of polar bond such that it's quite strong, but not to the same level as ionic interactions, but similar characteristics, okay, for our purpose. Van der Waals forces, van der Waals, we'll see what that really looks like in just a bit, but you know, they exist everywhere, okay, so everything has van der Waals. Intermolecular interactions, inter means between different things, okay? Intramolecular means within the same molecule, okay? So intermolecular interactions, essentially you're talking about how this one molecule of something interacts with another molecule of something, so it's intermolecular interaction. Okay, so as you can see in this particular figure, this is a very excellent example of hydrogen bonding in water. Okay? Yeah, okay, hydrogen bond. So hydrogen bond looks like that. All right, so covalent and non-covalent in biochemistry. So the macromolecules that participate in the structural and the functional matrix of life are immense structures held together by strong covalent bonds, like for example peptides, right? So between the amino acids, they're held together by these covalent bonding. So they're physically linked together, okay? Physically, chemically, okay? So they're linked together. So that is covalent bond, formal chemical bonds, okay? However, the 3D architecture of these macromolecules are determined by non-covalent interactions. Okay, so this is something that I want you guys to get straight. Okay, the general chemical structure, they are held together by covalent bonds. Okay, so they are made of covalent bonds. However, because these molecules are large, okay, large molecules, okay, they rotate and stuff. Okay, so of course they can start having different structures. Okay, so the 3D structures of these large molecules are determined or dominated by non-covalent interactions. Okay, that's important. Okay? So non-covalent interactions are critically important determinants of biomolecular structure, stability, and function. Okay? So throughout the rest of our entire semester, we're going to be essentially talking all about this stuff. Okay? So it's always the non-covalent interactions that determines, for example, what kind of a shape your macromolecule has. Okay? For example, proteins. Okay? Proteins are polymers of amino acids, okay? And these amino acids are held together by strong covalent amide bonds, or we call it peptide bonds, okay? So they're linked together by peptide bonds. However, the 3D structure of the protein and therefore the function, hence is therefore the function of proteins are determined by a large number of non-covalent interactions. For example, okay, have you guys heard of primary, secondary, tertiary, quaternary structures of proteins in general bio? You have, right? Okay. So you know that proteins have different levels of structures. So your secondary structure and tertiary structure, they're really held together by these hydrogen bonds, okay? In alpha helix, same in beta sheet, okay? So towards the middle of the semester, we will go over when a sequence of protein wants to be alpha helix, when they want to be beta sheet, okay? We'll talk about that, okay? So the importance of non-covalent bonds, so obviously in biochemistry, it's all about these non-covalent interactions, okay? So energies of non-covalent interactions typically are 1 to 2 orders of magnitude weaker than the energy of covalent bond found in biochemicals, so CCCH, that kind of stuff, okay? So then the question is, why are your non-covalent interactions important for biochemistry and life in general, right? Answer to that is they are essential because they can be continuously broken and reformed for dynamic interactions between compounds. Okay, that's a very important or that's a very worth noting feature. Okay, a lot of times you want to be able to temporarily separate something, put them back. Separate something, put them back. You want to give your chemicals or your life, okay, your processes, the diversity or the dynamic to change in time, okay? So that's important. All right, so if we look at an energy spectrum, okay, you got a lot of energy, not so much energy. Van der Waals, obviously, is down here, not very strong interactions. But where, if we look at around here, you got hydrogen bonds, okay? So hydrogen bonds, the energy is actually quite high, okay? So that means that if you form hydrogen bonds, your chemical becomes stable, is stabilized, okay? So formation of hydrogen bonds releases energy, okay? So these are the different types of non-covalent interactions that we will really be concerned with. You have obviously charge-charge, okay? Charge-charge, 1 positive, 1 negative, or 2 positive, 2 negative, doesn't matter. One very good example is amino group and a carboxyl group, okay? So these guys, you often find on, for example, amino acids, okay? So, you know, you got a lot of charge-charge interactions between amino acids. Sometimes you have charged dipole, okay, so one is charged, one is a dipole, okay. Charged, same, still amino group. Now dipole in this example is just simple water, okay. And water in this case, it's not charged, but it has a very polar nature, okay. So you have a charged dipole interactions. And then you got dipole-dipole, okay. You got charge-induced dipole, okay? So induced dipole is something like you have a molecule. This is it's a phenyl group, or you can consider this as a benzene. Benzene is typically not charged, not polar, right? We agree. Benzene is not polar. However, it turns out if you put a charge next to benzene, you will actually induce a charge. Like a short period of time, you actually can induce that charge. If you put a positive charge right here, it's going to draw the negative towards this end, okay, leaving that end of the molecule positive, okay. So when we draw it, we draw partial negative, partial positive, okay. It's not a formal charge, but it feels more negative on the left, more positive on the right. And then same thing, you got dipole-induced dipole interaction, same logic. If this guy is partial positive, you're going to put the partial negative around here, leaving this guy partial positive. Okay, that's fine. And then you got dispersion. Dispersion is van der Waals. Okay? It really involves a mutual synchronization of fluctuating charges. Okay, what that means is any molecules ever, okay, any, even though some molecules we consider non-polar, and that is because the electrons are balanced. Okay, there's no one side or another that has a lot of electrons. However, that does not mean that electrons are not moving. Okay, so electrons are always moving. So in the case of benzene ring, you got electrons moving around. So if electron is moving to the right, it's going to temporarily, okay, temporarily, you will have a partial negative on the right, partial positive on the left. It's going to cause the next benzene to have the opposite sign, okay? Because if this guy is negative, that guy is going to be positive. Simple as that. Okay, so this is van der Waals interaction. Okay, it's an induced dipole, it's a synchronized fluctuating dipole. Lastly, you got this very special thing called the hydrogen bond. Okay, so we like to separate hydrogen bonds from dipole. It's because hydrogen bonds is actually a lot stronger than typical dipole that you find. Okay, and essentially what you have is a hydrogen here, and this is going to be partial positive, partial negative. Okay, and this is partial negative. Okay, so this oxygen is naturally partial negative. This hydrogen is naturally very partial positive. So the interaction between them is very strong. Okay, so hydrogen bonds are very, very strong. So those things are the ones that keep your DNAs together. Those are the things that keep your protein structures intact. Charge-charge interactions. This is not physics class, so I'm just only showing you Coulomb's law as a way to remind you that force between any two charges is dependent on the charge and the distance. Charge between the distance. Right? So obviously, if the charge have opposite signs, force is negative. Okay. Now, turns out Coulomb's law is really ideal. It happens in vacuum. Okay. Of course, we're not in a vacuum. Right? When we're talking about biochemistry, things are pretty much always in water. Okay? So if you have two charges in water, you're going to have an extra epsilon term down at the denominator. This thing is called the dielectric constant. And essentially, it's the ability of the medium to shield charges. Higher the dielectric constant, lower the force between charges. Obviously, because higher this number, lower this number. So epsilon for water is about 80, okay? While for organic liquids, it's about 1 to 10, something around there, okay? So what this tells us is essentially that water will actually provide a shielding effect between two charges. How it works is like this. You have two charges, one positive right here, one negative right here, okay? If in a vacuum, they have a pretty strong attraction, okay? However, in water, you're going to divide that by 80, okay? That is because water has a permanent dipole, okay? So water is very polar, and water will spontaneously align themselves to your charges. For example, this guy's a negative charge. So water, the positive ends will point to the water, okay, like that. And for the positive charge, the negative end of water points to the charge. Okay, so in a way, this will sort of shield the effect of your charge. Okay, it will lower your force between the two charges. Okay, so this is what happens. Okay, and it makes sense. Why? As you have these partial positive, outside partial negative, so you sort of have a stabilizing factor by having water around your charge. Let's say your charge is very negative, it's not very happy, right? But if you have water and you give it some partial positive stuff to it, and your water becomes happier. So charge-charge interactions inside of a compound or between compounds, they can actually form this thing called the salt bridges. A lot of times it's essentially like ionic interactions, right? But we generally just call it salt bridges. Okay, so this is a key term that I want you guys to remember. salt bridges provide stability to structure. You get about minus 13 to minus 17 kilojoules per mole. Formation of this salt bridge provides this energy. Okay, it makes it happy. Now, again, negative energy means favorable. Okay, it means it becomes more stable. Okay, this, I hope I don't have to explain anymore. Okay, so every time when we say, you know, something like delta G something is like negative something, this means that it's very stable. Okay, it's favorable. A very good example is this. Okay, so this is a polypeptide. This is, for example, a peptide. That's another peptide, polypeptide. Okay, you got residue 1, positive charge, residue 2, negative charge. So they attract. Okay, they attract, right? And they're happy. They're happy together. Sometimes you also have this really weird thing where you got negative and negative. And then typically you're going to say, whoa, aren't they supposed to repel each other? Okay, typically yes. But sometimes you can put a divalent metal ion like magnesium 2+, calcium 2+. Okay, you're going to give 1+ to him, 1+ to him. And then they're stable. Right, so we're good with salt bridges. Now, dipole moment is pretty much another way of saying like polarity, kind of. And because there's a difference in atoms' electronegativity and molecular geometry, okay, so that's important. Geometry is also important. Electrons can be distributed differently within the molecule. So if a molecule has a difference in electron distribution among its ends, then the molecule is polar. Okay, for example, carbon monoxide, water, blah, blah, blah. Something that has a dipole moment or something that is polar, you can always have one end is partial positive, one end is always partial negative, okay? And it's always end to end. It looks at some of the dipole moments of some of the common chemicals that we see around. Obviously, carbon monoxide, okay, you have partial negative, partial positive. So you got a dipole moment. Carbon dioxide, you still have partial negative, partial positive, partial negative. But because the geometry is completely balanced, so you have no dipole moment. Water, you got partial positive, partial negative. So you push your electrons towards here, you have dipole moment. Okay, so on and so forth. Now, if you take a look at glycine, you have a minus charge, you have a positive charge. So the dipole moment for this guy is huge. Okay, it's actually very large because you actually have a separation of charge. Okay, where this end is not even a partial charge anymore, it's actually a charge, minus charge. So this guy is just minus, this guy is positive. Right? So the dipole moment is even larger. Make sense? Okay? Glycyl, glycine, and the question is, how come this guy is larger? Okay, by like double. Because as this molecule is larger, you have more electrons on it. So you can see how electrons can tend to cloud over here. Okay, so the separation of charge is even more obvious. Induced dipole interactions, okay, like van der Waals we mentioned previously. Like I said, induced dipole, if you put a charge next to something that is nonpolar, you can actually induce it to make a partial charge. Okay, this is important. Why? Because inside of a protein, okay, or inside of a complex molecule, things are 3D, three-dimensional. Okay, so some amino acids, they have acidic R group. Okay, side chain generates a negative charge. Okay, so you can have charges flying around inside of your protein. Okay, so by having charges there, they can actually induce dipole moments. Okay, they can actually induce different behaviors in your proteins. Okay, so that's important. Right, so the bottom line is what I want you to understand is anytime you have a charge somewhere, it's going to cause the environment to change. Okay, it's going to induce something. Okay， 可以哈，听懂哈？如果你在一个蛋白裡面， 某個地方有一個 charge，OK，、那這個 charge 呢會導致它 surrounding 的一些 chemical behavior 變得不一樣，就它會 induce 一些 chemical features. So essentially, it looks at two atoms. Okay, you got two atoms, and obviously you got a radius r. You cannot have any interaction below 2r. Okay, that's obvious because otherwise your molecules overlap. That's not possible. Okay, 就是空間上是不可能发生嘛。你 2r, 1r, 2r. You can't just have like r, right? So you will not have anything inside of the space. So then it turns out, okay, van der Waals, when you were in high school, you learned about that van der Waals is always attraction, right? Turns out that's not quite true. X-axis, distance. Okay? If you look at the distance between these guys, if they're too close, you still have energy of repulsion. The energy of attraction, starting right here, you increase your attraction significantly once you pass through like right here. Okay, so everything here is attraction. But right at the distance between the two atoms, you actually look at the black line, okay, the black line. You actually have a net repulsion. Okay, that is because it's too close to each other. Okay, so this is the interesting thing about van der Waals, right? So you can't be too close. Okay? Right next to each other, you actually have a repulsion. But once you repel to a certain level, they start to attract. Okay, so that's where you get this net energy of attraction. Okay, so this is the part where you get attraction. Okay, so that's that. So this is van der Waals. Now, for our purpose, it is pretty much attraction, as always. Finally, getting to the real business. Right? So this is hydrogen bonding. Particularly important dipole-dipole interaction is this thing called hydrogen bonds. And hydrogen bonding is not news to you. You will always have a hydrogen bonding donor, hydrogen bonding acceptor. And donor, a lot of times, we're also talking about this particular hydrogen. Okay? So for example, if you take an alcohol and a carbonyl, they can form hydrogen bonds through where? You can form through, this is OH. So because the H is partial positive, it can have a hydrogen bonding interaction with the partial negative of carbonyl. That's fine, okay? Or if you look at water, right, you got lone pair, okay? You got partial negative, partial positive. Partial positive binds with the partial negative of the other water molecule. Then you got hydrogen bonding. Easy enough. For biochemistry, these are the major types of hydrogen bonds found in biomolecular structure. You have alcohol to alcohol. So essentially this is OH to something like OH. Okay, so they can bind. OH and water, that kind of stuff. So it's like two hydroxyl groups. They can have hydrogen bondings, no problem. What we just saw, alcohol with carbonyl, you combine. You can have amino group or amine binding with alcohol, same thing. Amine binding with carbonyl. And then you have these other two where you have the amino group binding with the amine structure. Lastly, you get this amino group binding with a thiol. If I throw at you a chemical structure, you should be able to tell me whether or not they have hydrogen bonding. Okay? And how do you know if it has hydrogen bonds? When you have something like hydrogen attached to either oxygen, nitrogen, sulfur, they will be partial positive. They will be able to do hydrogen bonding. Okay? Right? And their hydrogen bonding acceptor has to also be one of these things. Okay? So hydrogen bondings are very easy to detect in a chemical structure. Properties of water. So hydrogen bond donors and acceptors in water. So two hydrogens, partial positive, two lone pairs, they give you the partial negative Here's my question for you. How many hydrogen bonds can each water molecules form? Probably something like 4, right? Because you have this guy is partial negative, partial negative, partial positive, partial positive, okay? So you can have 4 hydrogen bonds per water. And how the properties of water below can be explained by hydrogen bonding. For example, density. Density is pretty high, even though the molecular weight is pretty small, okay? And that, of course, is due to how you have very strong hydrogen bonding between water molecules. That's what makes it pack very tight. That's what makes it density very high. Simple. Boiling point, same idea. Because they packed very tight, if you want to separate them into a gaseous phase, you have to add a lot of energy. By adding energy, that rises your temperature. Dielectric constant, okay, because it has very strong hydrogen bonding features, it can shield charges very well. That's why it has a very high dielectric constant. Viscosity. Viscosity is how viscous this thing is. Okay, viscosity also very relatively high. That is because it binds very tight. Okay, surface tension, same thing. Okay, so hydrogen bonds super strong. As a result, it makes your liquid like to glue together. Water in ice form, in the solid form, it has a very regular lattice structure, means that you have 4 hydrogen bonds per water. Okay, it's very stable, a very nice structure. However, as you know, ice float on water. That is because when you have liquid water, you don't end up with 4 hydrogen bonds. You end up with approximately 3.5 hydrogen bonds per water. Why is that? Like I said, the more hydrogen bonds you have, the more stable the molecule is, right? Then why in water you don't have 4 hydrogen bonds? The molecules have too much energy as a result of temperature. Exactly. So when the temperature is above 0, okay, so the molecules are moving really fast, and it's moving really fast, it's going to partially counteract your hydrogen bonding structure. As a result, you don't have to have the 4 hydrogen bonds, okay, which makes water more dense. Okay. Properties of water. Water serves as the universal intracellular and the extracellular medium, okay, thanks primarily to 2 properties. Number 1, the ability to form hydrogen bonds. Okay, but you can form hydrogen bonds. Of course, you're polar, right? So these things are essentially the same thing. So substances that can take advantage of these properties so as to readily dissolve in water, they're called hydrophilic. Philic means loving. Hydro means water, so water loving. Okay, hydrophilic. The opposite will be hydrophobic. Water is an excellent solvent for ionic compounds. Okay, that is because the interactions of the negative end of water dipole with cations and the positive end with the anion in the aqueous solution. Okay, and it will cause the ions to be hydrated. Okay, like what we saw here. Okay, this thing, remember we saw that? And then when water surrounds a charge, okay, you actually form this thing called the hydration shell. The shell as in 壳嘛, shell, so this thing forms sort of like a little shell. The solution of ionic compounds like NaCl in water can be accounted for largely by 2 factors. Number 1, formation of hydration shell is super energetically favorable. So if you throw NaCl into water, you'll actually release energy. 2, the dielectric constant of water screens and decreases the electrostatic force between the opposite charge, which will otherwise pull them back together. If you have NaCl, right, salt, you throw it into a beaker of water, it becomes Na plus Cl minus, right? Now, without the hydration shell, this guy is going to go to Cl, Cl is going to go to Na, and then you reform NaCl, right? Obviously, we know this thing don't happen. That is because once you get Na plus, you have a lot of O like that. Okay? Like that. And then it sort of shields it, lowers the force between Na plus and Cl minus. So hydration shell, this is what happens. So NaCl, if it's salt, like this, and when it dissociates inside of water, then the chloride minus, like this, gets surrounded by your water. Okay? And the energy released in this interaction helps to overcome the charge-charge interaction that stabilizes the crystal. So this amount of energy is obviously, by having this interaction, gives you more energy than having this interaction. Hydration means water, right? Water shills. So water actually surrounds your charge. You'll see this picture again in 10 weeks. This is an example of how polar charge interaction is used in biochemistry. Okay? So polar charge interaction is frequently used in enzyme catalysis. Okay, so this is an example to show you how we catalyze a chemical reaction using this charge dipole interaction. Okay? So this picture actually shows you the first step in a protease reaction. So later we're going to talk about these things called trypsin, chymotrypsin, these enzymes that degrade peptide bonds. Okay? So in this example, you want to cut. In order to do that, the first thing you have to do is you have to generate some kind of a nucleophilic oxygen. Okay, so to do that, you have a organic acid acidic residue that is minus charged. Okay, so this guy is minus. So it's going to grab the proton to this end. So that's going to also make this guy partial minus. And then this partial minus is going to grab this proton. That makes this oxygen partial minus. And it becomes very minus such that it attacks this carbon, which is partial positive. So you can see a migration of electron charge. Okay, so this guy, very negative. It's going to cause electron go from this guy to this guy. This then becomes negative. So it's going to cause this guy to also be negative. Okay, now this thing is negative. Now it can attack that. So if you didn't have aspartate here, if you didn't have this negative charge, this thing does not happen. Okay, so this is how enzymes catalyze. This is why I mentioned an hour ago that says that the environment is very important. Okay, so for enzyme catalysis, the environment can actually affect each other. Okay, this guy is negative, it affects this guy then in turn affects this guy. Okay, so everything is sort of in a chain reaction. You do that, then you can actually generate a structure, a tetrahedral intermediate structure, where the electron can pop to this oxygen right here, and it's sort of stabilized. Why it's stabilized? Because you have hydrogen surrounding it that can make hydrogen bonds. Okay, so then it's stabilized. This is a stabilized kind of structure that makes the reaction able to proceed. This is the fundamental of enzyme catalysis. And then in addition to the shape. Another example of hydrogen bonds, silk, okay, or spider silk. You know, silk is a very strong material. Okay, so if you take the spider web like this and you zoom in, it looks like that. Okay, and it has a lot of these silk fibrils. And you take this silk fibril, zoom in, it actually looks crappy like this. Okay, and where you do get these little nanocomposites, okay, this thing. You zoom in this guy, and you see a bunch of beta sheets. So these are polypeptides. Zoom in, individual like this block, it actually looks like this. Okay, so very regular, a lot of regular hydrogen bonds. So it has a lot of hydrogen bonds that makes this material very strong. Okay, spider silk. So it turns out the hydrogen bonds between glycine, the glycine amino hydrogen and the neighboring chain's alanine carbonyl oxygen. So right here, right here, right here, here, right here. Okay? So you got a bunch of these hydrogen bonds stacked on each other. You generate this very regular beta sheet structure, and then it becomes very stable. Okay? So now, in terms of biotechnology, there are 4 companies and 1 university institutes. They're trying to make recombinant spider silk, okay, and using E. coli, of course. And then hopefully one day you can actually make dresses or bulletproof vests out of spider silk. Hydrogen bonding, also DNA. This is no surprise to you guys. Thymine always bind to adenine because they have 1, 2 hydrogen bonds. Cytosine always goes with guanine because you got 1, 2, and 3 hydrogen bonds. Isn't that surprising? Okay, so DNA also uses hydrogen bonding, right? So we just saw 3 very good examples. Number 1, enzyme catalysis. Number 2, protein structures, okay, for mechanical structures. Number 3, DNA information storage. So all thanks to your best friend hydrogen bond. So the last thing that I want to talk about today is the hydrophobic effect. So this is something you know. Okay? You know this when you're 5, maybe 3. Okay? You know that if you drop lipids like oil, like cooking oil, in water, they form aggregates like this. So this just tells you that, hey, oil doesn't dissolve in water. Okay? Now, this is something where we can generally refer to as the hydrophobic effect. Okay? Hydrophobic compounds aggregate in aqueous solution and kick water out. Do you guys know what's the scientific reasoning behind this? It's actually an entropic effect. So we know in terms of things happening in life or in the world, it's usually due to free energy, changes in free energy, right? If delta G is minus, you have a favorable thing that will happen. Hydrophobic effect is actually an entropic effect, and I'll show you why. Nonpolar substances like hydrocarbons are non-ionic and cannot form hydrogen bonds, so they have limited solubility in water. Such nonpolar molecules are called hydrophobic or water-fearing, or sometimes people also refer to them as lipophilic, meaning fat-loving. So this is the reason. When hydrophobic molecules do dissolve in water, they're not surrounded by hydration shells. They're not. Okay? Even though this looks like a hydration shell, it's not. Rather, you form these regular water lattice structures, sort of like cages that looks like ice. So they form very regular structures that looks like ice around the nonpolar molecules. Okay? So this happens. This is really what happens. So this ordering of water molecule extends well beyond the cage, corresponding to a decrease in the entropy. It actually makes entropy of water decrease, not the entropy of the stuff inside. The entropy of water decreases. So if entropy of water decreases, is that a good thing or a bad thing? Or not good or bad. Favorable or non-favorable? It's non-favorable. It's not favorable. Okay? For entropy never wants to go down. Entropy always wants to go up. Okay? So as a result, if you have lipids dissolving in water, you generate a lot of these cages. So as a result, your lipids do not want to generate a bunch of these structures. So the lipids will come together, and then it minimizes the amount of these cages that you have to form. So this is the hydrophobic effect. Okay, so this actually explains why your lipids always come together. Because if they don't, you will have lipid, cage, lipid, cage, lipid, cage. So you have a lot of ordered water. So delta S is low. As a result, spontaneously, in order to increase your entropy, those oil droplets will come together and form a larger oil droplet that only has to form one cage. So the delta S, the process delta S increases. S is low. S is less low. I don't want to say high because it's not really high, okay? It's just less low. So as a result, this process delta S increases, okay? So this explains hydrophobic effect. Okay, so hydrophobic effect is really an entropic effect, okay? So entropy of who changes? Not of the lipid, of the water, okay? That's it. That's all I have for today.